feel what's going on.
Yeah.
We got halfway through the Gaussian.
Yeah, that is a good example to demonstrate that sometimes if you that is a trick the theoretical physicists or theoreticians use to sometimes instead of focus on particular integral in the lower dimension, they go to higher dimension. That would make things easier to tackle mathematical operations. And so these that's why I planned last time to talk about this integral, but it turned out that we have to do some preparation before that.
Yes, right.
I think we can focus on this integral. I can simplify this integral as such. So that is why. That's why when you study statistics, I think it's in the high school level, we never ask students to solve this integral. Okay, x squared dx. Okay.
Yep. I just joined on the other device.
Okay. So we have last week discussed the various variation, but this is the form where we would like to tackle. Okay. Yep. And of course, you may argue that the actual form of normal distribution, we got this. So this is the form. So probably apart from constant, we got this x take mean divided by standard deviation square. All right. So ultimately, we can just do some transformation to get this this form.
Yep.
And so basically, if we can integrate this one, and we should be able to solve the all the this table, the p what is called as a p-value or p what z-score table. So that's why that's how people actually actually in history this is some great mathematician involved to solve this integral. I happen to find that there's actually Jorna actually involved to solve this integral.
Right.
And just to remind you, and relatively speaking, another integral is easier. So if that will involves you to calculate the mean, you see. So do you remember last week we spent some time to deal with this integral?
Yes.
It's turned out this is much easier because in this time I just remind you that is very useful technique. So what we do is we just put this x inside the d, so that will become x squared and about dx squared. Okay.
Yeah.
So because you see when you do the dx, so actually you know what? Once you can rewrite the first derivative into this form, so that's the dx. I can see. Once you know that we can simply rewrite df in this form, then you know almost everything about calculus. Right?
Yes.
So this just remind you. So this is called the first derivative, and it's called differentiation. Okay.
Yes.
Differentiation. Yes. So basically, what we have done here is the reason we can do so, of course, apart from constant, because a good example that we discussed before, you tell me what is a dx squared in term of this general. I would like to be involved this discussing. So how can we work out the dx squared? Although we often spend time to find first derivative first.
The dx squared.
Yeah, does that make sense?
Yes. So what, like, let me think. dx squared. df.
So the term is called differentiation of x squared. So this is called differential distribution is the same. Differential differentiation.
Yes.
Of x squared. So that is a term we.
Uh-huh. But that is right. But that is different from the DF. So
Well, in this case, f is equal to x squared. Good point. So you
yeah.
see, when we write this f is just a function. Can you see?
Yep.
S could be represent any function. So f just represent a function.
Mm-hmm.
By the way, this notation also is introduced by Orna. It's it's a great mathematician.
Yes. So sorry, let me just scrapbook down here for a second. So we've got
Sure.
this equals df dx, and therefore df
That's
equals
right. First derivative.
x dx.
Yep.
And we're saying we're going to add a squared.
Oh no. No, dx is different from dx squared anyway. No, dx certainly, can you see? I just probably write down some detail here.
Mm-hmm.
The reason I can do so, I just shift. Can you see? I put this apart from constant. I have to multiply. I have obviously because I know that the result. So
yes.
We have divided by 2 here somewhere. Can you see?
Yeah,
yeah. So basically, what I did is I put the x closer to the dx.
Yeah,
then I rewrite this. I rewrite that.
Yes. I suppose what I'm not sure about is let's just say we've done that. I don't know what the implication is here for the left-hand side in general.
Oh, you can consider this df is just interval, tiny decimal, so small it's actually infinitesimally small, and this interval can be written as his first derivative with respect to x multiply another interval called x. Is that does that help you, this form? Third, differentiation is just interval of function, you see.
Yes.
Small, tiny, very infinitesimal interval.
Right. So what does that imply for this?
Well, that is I'm looking for this answer. Can you see?
Yes.
So according to your, I use your formula, all right? And df is equal to f first derivative dx. Do you agree?
Yep.
In this case, f is equal to x squared. Therefore, we found the first derivative first. Can we?
Yep.
Can we find the first derivative in order to use this formula to find the df?
Yeah, sure. The first derivative is 2x.
Yep. Okay. Can we substitute that into this formula?
Yes,
so we can substitute that into the formula.
2x squared.
Not yet. Not yet.
Yep.
Not yet.
Okay. So we have 2x dx.
That's right. Yeah. So we got this. We got this term. So this is a function. This is core. Can you see? This term x plus dx is proportional to the first derivative, the differential. Do you agree?
Yep.
So what does that mean? That tells us that in this function that we say that this is if you get through these ideas, then you can understand the calculus well.
Can we further simplify this though to just say
yes,
this equals 2dx squared?
Well, then nearly, but you have to make sure why there is a 2 here. How do we handle this 2? Yes, good. Yeah, why not? Yeah, okay, you're right. Go on. Yes, actually, I read that. You're right on. Yes, you are correct.
Right.
You're correct. So hang on, I have double check that. So this is certainly correct. Okay. Now, if you whether you multiply 2 or divide by 2, I'm not sure. How can we evaluate this one? So your conclusion, right? It's it's a 2x, and if I put a 2 here.
Yes. How does that square with this? Right.
Well, you can repeatedly use what can you do? You can repeatedly use this formula. because the dx square, can you see? Can we just follow your idea this time? I change the color. I follow your idea. If I continue, can we just copy your what, right? And then I use this formula again. Can you see? That formula will take as 2x, which is the first derivative. Okay. And then that is and then we got the dx. It turned out it became 4x. So it's not right. The proportionality is wrong. So what happened? What happened?
Yes.
So this transformation. So from here to here, you have to think twice. Okay.
What 2x dx? Oh, I see, because there's brackets. I understand. Sorry,
no, it's not bracket. It's just the coefficient is not equal to the 2 now. Can you see? We're starting from the 2. Can you see? Pay attention to this 2 here. We got 2 here. Can you see?
Yes.
But we turn out to got 4. So obviously something wrong with this transformation. Can you see? You see, we got the 2x dx, but now it's turned out to become 4x times dx. So something is wrong.
I see. Yes, but we need to get rid of this too somehow.
Oh yes, that's right. So what you do is we have to from here to here. So this is a question. So we have to do something about this number. Okay. Can we just this is very interesting because can we use this tiny table here?
Yep.
So we are, see, put it another way, we are looking for, can we, this is probably easier for you. Can we use this notation for the first derivative? Can you see?
Yep.
So if this is the first derivative, so 0, if we substitute this x squared here, that is f equal to x squared. And then, of course, we got the same result, it's 2x. Can you see? We just use different notation, okay?
Yep.
So therefore, if we just use simple algebra, if we just multiply dx on both sides.
Okay.
Okay, I'll get your result. Yes, you get your result. So df is equal to 2x multiplied dx. You see?
Yep.
So in other words, we know that dx squared is equal to 2x dx. Does that make sense?
Yes, that does.
Does that?
Yep.
So the answer here, return to our answer. So this will become 2. You see?
Yep.
2x dx. All right.
Yep.
Now return to this question. We cannot jump to this one without divided by 2. That's why how can avoid this trouble? Can you see? You notice that I divided it by 2, knowing that otherwise we will got an incorrect answer.
So do we to cancel this 2? Oh, wait,
well, this 2 is added. Can you see? We know because if I just write down here, so in other words, from the information here, we know from the result that is correct, we know that x dx does not equal to dx squared. All right.
Yes.
But what we can do, if you multiply 2x dx, it does equal to dx squared. Do you agree?
Yes.
Now, in the absence of, in this case, we have used this, we have called this 1 unit, can you see? Because we need to borrow the 2 here. So, but the coefficient here is 1. What can we do? We can rewrite this one as 2 divided by 2. Can we?
Yep.
So we give this 2 to that. We build this 2x in order to write this form. What has left is 2. Can you see? Divided by 2.
Yep.
That is a trick using algebra. Can you see?
So do we end up with 1 half x dx equals dx squared?
Not yet. No, the correct answer is 2 divided by 2. And we rewrite this as half. Can you see? This just building something. Can you see?
Okay.
In other words, this house have two windows. We all have one, all right? So we just so we just borrow the two, but divided two at the same time.
Oh, sorry. Let me rewrite that. What I meant to say was, sorry, if I get rid of this for now, this.
This page, let's go to next page. It's a bit crowded here. So basically, we're trying to so we just recall this relatively easy integral, right? I just jump to the more closer form. We got this form, x dx. Oh, by the way, this one is proportional to the mean value, you see, or expectation value when we use the normal distribution. Right? Now, so the question is how to rewrite this part. We cannot. We know that dx squared. We have just worked it out. It equals to 2x dx. All right. But what we have here is just half of that. Can you see? Can you see? This is just half of dx. Now, how can we get this coefficient correct? Then what we can do is often we just borrow. We can just recall the unit. You see, the unit is just number. So remember, in algebra, one can be invisible, and also one can be written as a ratio of two identical numbers.
Yep.
See. So in this case, so we because we need two, so we build the two. Okay. If on the other hand, if we need a three, we use a 3 divided by 3. Okay. So that's how this algebra. So in this case, so recall this is just one, okay, invisible one. Yep. But then after that, we know that if I just put the denominator outside, inside will be exactly, or I just want to get one more step. That became 2x dx. You see, we know 2x x is what is this is as a whole is equal to dx squared.
Yes. This and this
coefficient. Yeah. So this is this. So basically 1, 2. So we just shift the 2 outside. Can you see? So that's why we got this half in the front. Okay. So that is how we use the algebra. Can you see? Therefore, we can say that integral became x squared and dx squared. Okay. Now the reason we built this dx squared because I see the opportunity to introduce another new variable, which can make this integral easily integrated.
Yes.
Because this x squared can be represented by a u. Can you see? Yep. So we just introduce a u equal to x squared, and this integral will immediately become very familiar integral. Can you see?
Yes.
In EU du. Can you see? And that is nothing but just half EU plus the constant. Solved. Can you see?
Yep.
So that's why I call that is in the normal distribution. If you're looking for the mean expectation value, the integration can be done easily by using this substitution method.
Yes. Okay.
Now, return to the target. But how do we solve this one?
Okay.
In the absence of x, can you see? How can we solve this one? There's no shortcut. Can you see?
Yes.
Because it's impossible. So that is the only relevant formula is here. Okay. But this is here is got a square here. We cannot solve that.
Yep.
Now, to solve this question, so in history, so we have to, although they are dealing with this is dealing with one variable function. Can you see? So you can see this. So this can be written as fx. Can you see what I read it properly? Yeah. The form is very important. Can you see? So basically, what we are dealing with one variable function. Okay. Now, or because in algebra we can use any letters, so therefore this integral can also written as a slightly different form. Do you agree?
Yep, same thing.
Doesn't matter. It's the same thing. You can say you can use alpha, beta. It's the same. So then they say, well, if that is the case, if that is the case, then we can argue that if we multiply them, so we can work out the integral square first. Can you see? If you integral square, so what we have done, I probably spend some time. So this is the first part is x squared dx. Can you see?
Yep.
Multiply the integral, that is y squared dy.
Okay.
Can you see?
I don't follow this part. So
well, this is so there are two integrals. Can you see? There are two integrals. See? Yep. So first integral is this one. So this second, probably I put this. Do I put the? Can I put sub x here, sub y here? Or don't have to. They are the same thing. Okay.
Yes.
The same thing.
This
so
is just
they just put the two interval. Can I just square them? Okay.
Yep.
So this is the first part, the second part. Okay. And this integral can also be written as, can we put the integration notation in front? And that becomes the ex squared multiply y squared. And this that become dx dy.
Yep.
So in other words, we have the rewrite this form as a two variable function. In this case, f is a function of both x and y. So I will tell you why I do this transformation or rewriting, because in this way, we do you remember the graphical meaning of this integration? Yes.
Are we going to invoke the? Are we going to add the two partials?
No, we are going to if they have probably put this. Can we just put a and b before we invoke infinity? Can you see? Can we use a and b, right? And so a and b is a and b. I use a definite integral, a and b, and a and b. Okay.
Yep.
So you that means from a to b. Okay, from a to b, from a to b. So graphically, I think we have drawn this diagram before. So what we are when we see this integral with two variables, so what we are trying to work out is this volume. Can you see? If this is x, it's 3D now. Can you see? X, y are variable. Okay. Although usually sometimes we use, in many cases we use y as function. But in this case, y is independent variable. There are two of them. Okay? So basically, the graphical meaning is that you x from this this is domain for the x. Can you see? And this is domain. We just put all the assume both a and b are positive.
Yep.
So basically, what we are going to do in this case is to work out this the volume. Can you see?
Yes.
We're trying to work out this volume, and whose surface is irregular. Can you see? Whose surface is irregular.
Yep.
So this is probably is not flat. Okay, it could be curvature. It's curvature. Can you see?
Yep.
So, so you can imagine that we of course, if we just go to very small, this a and b. Can you see? From a and b. If of course, if we just use this idea of the infinitesimal, can we see? Can we pick up any of them? Can you see? If I just use tiny area, can you see? So this tiny area, dA. So tiny dA can be simply written as dx multiplied dy.
Yep.
You see that?
Uh-huh.
So this is our the area. Can you see? It's a cross section. Can you see? So this, you can see this is a cross section area.
Yep.
So the height in this particular value, so because this area is small, the height can be considered as a single value. So which is just fx. So this would be the height. Can you see? Single value height. So therefore, you think we understand now the whole integral here. So this so the whole thing here. So this integral will represent this area.
Or is the integral the area or the volume?
The volume. Sorry, this volume will although it's a double degree, the whole thing will represent the volume. You're right, volume. Okay. So we are going to calculate the volume. Can you see? To do so, and we have to use this. We have used this Cartesian coordinate. Can you see? X, y, dy, dx. Okay. Now, if I just pay attention to this tiny area, can you see? So I just highlight this area. It's very small. Can you see?
Yes.
And it's so small. And then I try to introduce another coordinate. Okay. So this time, I will assume that if you it's called the Pono coordinate. When you're dealing with mathematical form, sometimes they go to Pono. The Pono, can we just give you a introduction of Pono? How do we describe the Pono? Can you see?
Yep.
So then we just look down the XY plane this time. Can you see? If you just look down from top, so there's your eye here. So you look down. So you will see X and Y. Okay. X and Y. Now at a particular point P, can you see? So this is a P. You can use X and Y to represent this position. As we did now, you see. Alternatively, when you start vectors, when you start a complex number, we can also introduce another two variable to describe this position.
Okay.
So if I just draw this one, so we can also use this distance from origin. Can you see? So that is called a Pono. It's called the Pono coordinate. So this is our R. Is R. Another variable is a theta. You see? So in this way, this position can be represented by, so this is X, can you see? This is Y. Now, a little bit of trigonometry.
Yes.
How do we describe X in this coordinate? And how do we describe Y in terms of the R and theta?
Is it R sine theta?
R sine theta for Y or for X?
For Y.
For Y is, you're right. So R sine theta. Yeah. How about X?
R cos theta?
Yes, you're right. Oh, good. Can you see? In other words, we can equivalently to describe this position, this point, can go to P. By either XY or R and theta. Okay. Now, let's just imagine if we assume in this area, do you remember we are trying to work out this tiny area now, not just one point. Can you see? Of course, mathematically is a point. It's very small. Can you see? So I didn't draw square because when everything getting small, there's no difference between square and a circle. Okay. Does that make sense? Now let's imagine this is very small. So this is very small, infinitesimal, very small, very small area. Okay. Actually, it's infinitesimally small. Okay. So therefore, we can argue that, well, probably we can draw another diagram, the larger one.
Yep.
Because I want to find some relation between these two. So if I just, this time, we can consider that there's a slightly a variation of the R, or theta, sorry, variation of theta first.
Mm-hmm.
There is a slightly different of R, theta, can you see?
Yep.
Then also, maybe made to for you, we just make this area not too small, finite, okay? You can see it.
Yep.
So let me draw this diagram. So this so from here to here is just theta. So this is R theta, can you see?
Yep.
And that will be just R plus R theta. That would be the theta plus delta theta.
Mm-hmm. Yep.
This point. Similarly, we can argue that we can also consider the variation of R. I'm trying to build the tiny dA here. Can you see?
Yes.
So that is, yeah, you know what I mean? Okay,
yes.
So basically, the idea is to draw your attention. How do we rewrite this area?
Mm-hmm.
Okay.
So it's going to be R theta and R plus dr theta.
Multiply
sorry, like
can you write down? So this is theta. So this is theta. Yep. So this is d theta.
Yep. So this is going to be
this is R. Yeah.
R plus dr theta.
Yes.
And then this one is going to be R plus dr d theta.
Yes, that's right. Or theta. Theta plus d theta.
Sorry, yes.
You're right. You're trying to pinpoint this 4 point. Can you see?
Yep.
4 point to make the kind of square, right?
Yep.
It's a rotated square. Okay.
Mm-hmm.
Okay. So basically, the reason I do so is because when we do, if we just use x, y coordinate, I probably put this elsewhere. Can you see? Mm-hmm. When we found the tiny area, if we use the Cartesian coordinate, on the other hand, so I just highlight this area. So if that is a preparation for making that integral, you see. So if we use x and y as a variable to describe this area, and this side would be simply dx, can you see? And this side would be dy, do you agree?
Mm-hmm.
So in other words, in this case, so in Cartesian coordinate, dA, the rate area, is equal to dx dy. Okay. Mm-hmm. Now, the question is, what is the formula for dA in the polar? It's called the polar coordinate. Polar coordinate. So in terms of R and theta, so what is the dA in this case?
We've got to put it all together. So dA is going to be.
No, we need to find it. We are not looking for the coordinate. We need to find the distance now. Do you agree? So yes. What is the distance of these four sides?
Well, is it? I mean, will it still be this multiplied by this though?
That is a dr, isn't it?
Yes.
That is a dr. Can you see? That distance is just probably let's get right to the results. Obviously, that's increment dr.
Yep.
But how about this side? Can we just, that's important. How about this green side or this side? Very close, can you see? How about the green side?
Is it not just d theta?
It's not d theta, you have multiply r.
Yeah.
So basically you have multiply r here. I will tell you why. So you have multiply r d theta. So there's two sides here. Now, then we'll just give you a relevant formula. So this is so when we're dealing with the Cartesian, we're dealing with the polar. Can we draw the circle here? Can you see the circle here?
Yep.
And if we want to find this So if this is if you are looking for the this called arc. So this distance called arc. You see, just draw one of them. Just draw one of them. So that's not necessarily unnecessary to do. I just draw one position. You see. So if basically that is a formula, if the radius is r, and this angle is theta, so this is called arc. You see this. I use this green color. So this curve, can you see this green curve, part of a circle, right? Right.
Yep.
It's called arc. Okay, called arc.
Mm-hmm.
So this arc can be simply written as, if you use if you don't use a degree, if you just use radian, see, is that equal to product of r multiplied theta.
Okay.
So that's why. So that's why from this formula you can see the ds, if r is constant, ds is equal to r theta, d theta. Can you see?
Yep.
Or you if you of course you can use a partial notation. You can say delta. You can use the ds or del s and partial derivative to theta. Can you see? Or equal to r.
Yep.
Can we? Therefore, this del s is equal to r multiplied delta theta. Can you see?
Yep.
So this when things getting very small, whenever you see this relation is equivalent. Okay, they are just equivalent now. Can you see?
Okay.
So the important thing is that from these two different coordinates, we obtain this very important relation. So based on these two formula, so we have the dy dx dy is equal to r. Can we put r in front? R theta. So r dr d theta. So that is a relation we are looking for in order to continue our integral here.
Okay. Yep.
Okay. Now on the other hand, there's one important. And on the other hand, so what is this term? Do you remember? In this term, we have this term, rx squared. Before that, can we just go back to this formula here? Can we just rewrite this integral as use some index law, because it's a product? Can you see?
Yep.
That can be simply written as a sum of the product of the index. Can you see? Because the product, okay? So therefore their index must be the sum. Right?
Yep.
So in other words, they said we found the formula to replace dx dy. Okay. Secondly, we also need to replace x squared and y squared by theta or r. So what is the simple relation between this x squared plus y squared?
Given that they're the same.
Yeah, they are same point. Can you see? Say this is p. The point is p. Given the same point.
Yes.
So that it should be x, y. Can you see? This position must x and y. I give you the apparent. I draw this triangle here. So this is x. This is y.
Yep. And we're looking for this.
Yeah. What is this result? What in terms of r or theta? In terms of r theta, what would be the result?
Okay, we've got
little bit of trigonometry.
Yes. So do we have x is going to be r cos theta?
Oh yes, that's right. You can still do that. Yes, you can follow that definition. R cosine theta. Yes, you can do that.
Yep.
Okay. How about the y?
Plus r sine theta squared.
Yeah. Okay. Can you continue? Can you simplify this equation?
Yes. So from here, It's going to get big if I start expanding.
Or you can factorize. Can you see the cofactor?
Squared.
Yes, r squared is cofactor.
Yep.
Yes.
So we've got r squared.
You put it outside. Yes.
Is it
Cosine square? Yeah, cosine square. Yeah.
plus sine?
Put a square here. Yeah, put a square here.
Yep.
Okay. Okay. Oh, that's how. By the way, that's how to denote the sine square and cosine square. Okay. When you say this square, and you can just put the index just at the top of this last letter.
Okay.
Can you see?
Yep.
So what is sine square plus cosine square? A little bit of geometry, trigonometry.
Sine squared, but I'm not sure.
1.
Ah, r squared.
Yeah. Actually, from this triangle, you can do it without go through the definition. Can you see? In this triangle, if you look at this triangle, what can we draw it? Blue color. Can you see this right angle triangle here?
Mm-hmm.
It's a right angle triangle. If you simply apply Pythagoras rule, the theorem, that you can get this conclusion directly. Because x squared, so you have triangle, can you see? They just draw this triangle somewhere else, can you see? This is a triangle, right? This is not this right angle triangle, can you see?
Mm-hmm.
So in this triangle, and this hypotenuse is r, can you see?
Yep.
So this one is x, and this is y. And this is a right triangle. This is a Pythagoras theorem you can apply. Yeah, ABC. Yeah, ABC. Yeah.
I see.
So in conclusion, this is just r squared, isn't it? So this is our second relation. This is equal to r squared, right?
Mm-hmm.
Okay, we got the 2 equations now.
Yep.
Then we are in the position to solve this problem now. We'll start to write this next page. So we know that the integral square can be written as, I just copied our result. That is from A to B, from A to B, from A to B. That is EX squared plus Y squared dx dy.
Yep.
And then we know we can do substitution. Okay, can you do substitution this time? Can we just use our 2 formula? Dx dy can be written as r dr d theta, and x squared plus y squared equal to r squared. So this is the 2 important relation you can apply. Where is the e? Exponential. This is still has exponential. We can only change the index. The e is still there. Yeah. Okay. Make it clear. So that is when you write exponential, you can either write e use a subscript, or you can use this exponential, that is original notation.
Let's do the r squared.
That's right.
Yep.
Okay. So the integral here is changed, can you see? And then we have to consider that. So in this case, when we deal with the standard deviation, we actually, the integral is from negative infinity to positive infinity, right? And because it is symmetrical, can you see? So basically, it's another thing. I think some detail here. I need to explain. So if you have if this equation is even function, let's just do some one-dimensional function. So if you have the of course we know that the normal distribution. So this is density function, probability density function. This is one-dimensional, right? So we know that the function will look like bell shape. Can you see like this?
Yep.
So this kind of equation function is called the even function. See? So both sides, the area is positive. Can you see?
Symmetry. Yep.
So in other words, so in this case, so that's f in our case is ex squared. So is an even function, even.
That's 0.
Not 0.
But
yeah, I got it. I write the odd function side by side. Okay, I put odd function side by side to give you some comparison. If it is just hypothetical function, okay, and say it could be the first derivative, doesn't matter. We just choose this graph. So this type, if you got this function like this.
Oh, sorry. Yes, that's 0.
So that would be the total integral would be 0. Can you see? So this one, so this side become positive, this part is positive. Can you see? So in this case, g is called odd function. Okay. Odd function. As a result, if you use integrals, so therefore, if you are looking for integrals from positive, negative, positive, to the positive infinity, right? In the first case, for the even function, that will just equal to double, and then the integral can start from 0.
Yep.
Can you see that?
Yep.
On the other hand, if that is odd function is a symmetrical region domain, and without doing detail, we can categorically conclude it is 0. Okay, so that is the difference between even and a function. So therefore, we are dealing with this function. So therefore, what we can do is we can before we go, can you see they got 2 variables? One is theta, one is r. So we have to rewrite that one. So we put the theta here because theta, we can just put the theta over here. Okay.
Right.
Theta, this I can put the integral of r in this form. Er squared r dr. Can you follow me? I separate these 2 variables. Can you see?
Yep. Could at this point, could we change it just to x and y and it would make no difference? Or does theta have to clearly be?
Oh, we took all the trouble to go to there to get rid of x, y. Why do we have to revisit the y? The reason you didn't notice that the solution is there. Can you see? Do you remember that we have today repeated their calculation of what we called I1? Do you remember? Do you remember this integral we just solved today?
Yeah.
So by introduce a new variable, we can somehow to avoid this this is a challenge. So this is a difficult integral. So that is idea here. Can you see? I told you so. So basically, can go to the beginning. So this is a challenge integral. Can you see?
Yeah.
And relatively speaking, I1 is easy. That's why we went back and by using the substitution method, we solved this integral called I1. Okay. Now it's turned out that once we transform this integral from the Cartesian coordinate based on x and y into the polar coordinate, which is dependent on r and theta. Then we got this same form. You see, the first integral is rather simple. I tell you what, the first just use this because you see this the integration and can be cancelled. Can you see?
Yep.
Okay.
Oh, okay. Yes.
So in other words, we know this answer now. Do you remember what is the answer?
Yes, we need to put a half.
We put it a half, and what is our answer? Let's just check. I1. Yeah, we just half, and it's a u square. Can you see? So this is our answer, isn't it? Apart from a constant.
Mhm.
So in other words, this integral can be directly written, just put the 2 in front. We can solve that one. So basically, you know that, so this finally, this integral can be written as theta, can you see? That is variable. For the r, we have divided by 2, okay? And then multiply the e to the power of r squared, can you see?
Yep, plus constant.
Plus the constant.
Yep.
Can you see you solved? You solved,
Yep.
okay?
Okay.
Of course, then of course, if you want to go to detail, because this just tell us the mathematical form. So this one, so the I square, it can be written as this form.
Why is this one? Because the original integral
Yes.
about the square,
Yeah.
did we not get the same answer?
Well, of course, it should be different. You see that this is very clever way to solve this challenging one. We, of course, they are different. Can you see? I just show you something. I just summarize what we have done here today. Give me one moment. We know these two integrals are different. Okay, so we are not expecting they are equal. Can you see? So these ones, the first one, which is ex squared x dx, is turned out is simply equal to half ex squared, apart from constant. Okay, sorry, x squared, not x squared. Can you see?
Yep.
And this integral, which is different, of course, we wouldn't expect they have the same answer. Can you see?
But
okay,
but don't they end up with the same form?
Very closely, not exactly. Oh,
Okay.
by the way, why do you know why there is a pi? Do you remember when you're dealing with normal distribution, right? We just write for the z standard deviation. Do you know why there is a 2 pi here? Why there is a pi?
Because of something to do with the circle.
That's with the theta. You are right. With this theta, can you see? And just give you some, there are a lot of implication here. So basically, when you use the normalization condition, we know that this constant, so we know that, so this constant, so here is come from this integral from negative to positive, right? Yep. So this square, or another thing, the square root. How can we get the square root alpha pi? Let's just summarize what we have obtained. Just remind you, this is clearly not equal to I1, all right? That's for sure. Yes. There must be some difference. Yes. By introduce a new variable, we just introduce I square, we will end up with this new formula, that is a theta, you see? I just write the result now. That is put it half here, and that will be equal to E and R squared.
Okay. Yep.
Okay. Yep. It is different. Okay. In other words, apart from the constant, so therefore, the second this integral is actually equal to the root of everything. Can you see? Theta half and e to power of r squared.
Yep. Okay.
So of course they are not equal. Okay. The reason I mentioned is that we can have a shortcut, because in this case, so we have to, that's again to return to the mathematical form. When you see these forms are identical, okay, so these mathematically they give the same. So that if that is a half e x squared, then you can change this variable as r. Can you see? Yes. Then you could get the same form. The result, the form is very important. Can you see?
Yes.
Number one, certainly these two integrals are not identical.
Yes.
Although when we derive the formula, we use the result of the first integral, can you see? But that doesn't mean they are equal, okay, at all. Now, to really appreciate it, you have to really check what is how do we work out this integral here. So when we just that is something you need to get clear. So basically, if we use the Cartesian coordinate, okay, we are supposed to integrate from all this distance. Can you see? Okay.
Yep.
This actually, the size of this circle must be infinity, right? Of course, the value will fall down very quickly. So in other words, so this domain is x is from the, if you use a Cartesian coordinate. So x is between, so x is from negative infinity and to positive infinity. And also that's y, you see, negative infinity and the positive infinity. But by just introduce focus on the positive side, then we can only look for this quarter, can you see?
Yes.
So in this one, so this is so another domain to integration because it's a even function. The domain will change from 0 to positive infinity, and y is also from 0 to positive infinity. So if you just look at this quarter, if you look at this quarter of circle, these are x, these are y. Tell me, what is the domain for theta? What is the domain for theta in this case? So what is the domain for theta in this case? When correspond to this quarter only.
0 to 90?
Yes, half pi. Can you see the pi come up? Can you see the pi?
Yes.
Can you see?
Yep, I see.
And another thing, and say, how about r? R is 0, isn't it? Because when r equal to x, y equal to 0, r is also equal to 0.
Okay.
And that's equal to infinity. So in other words, if you want to solve this problem, you really, what you have to do, you have to utilize, can you see? That is that will give us I directly jump to the definite integral, can you see? So theta will be from 0 to half pi. Put this one. So you have to from theta, so I can say theta equal to 0, r equal to 0, to theta equal to half pi, and r approach to infinity.
Yep.
So you have substituted that into this formula. Anyway, yes. that is how you simply use integration to simply to derive this fact over here. This factor, they got a pi, they got a square root. That is because we cannot integrate this normal distribution function directly. We have transformed into the polar coordinate in order to solve this integral.
I see. First time I've seen polar coordinates properly. Interesting.
Well, I think we can yeah, if you wish, we can spend some time to get. I think you have encountered before when we start a complex number.
No, that's right. Yes.
Okay. When we that's where we introduce this polar form. We got a theta and r instead of the x and y. Anyway, this is just a good example to show you how to we use apply the two variable calculus to solve some of one variable function integral, which is I can tell you, to my knowledge, I haven't seen the second method yet to solve this problem.
Oh, really? The polar method?
Yeah, without invoke the polar. Maybe there are some other algebraic method, but this is relatively straightforward. Relatively.
Yep. Yeah.
But
Great.
anyway, that gives you some impressions that how to apply the calculus into the into in this case, you can see it's just statistics, normal distribution.
Excellent. Well, I'd love to next time just keep doing some live problem solving. I find it's the best way for me to lock it in is to just solve stuff.
Yes. Today
Yep.
we're emphasizing the form, all right? We're emphasizing
Yes.
the form. Then next time we can use some numbers to give you some confidence.
Great. All right, that sounds good. I'm looking forward to it.
All
Thank
right,
you very much.
I will see you next time.
See you next time. Have a good week. Thank
You
you,
too.
Dr. Young.
Goodbye.
Cheers.
Goodbye.
Bye.
To stop sharing.